Power transformers perform the vital task of changing voltages from one level to another. They're essential for the efficient and economical transmission of power over long distances. In this program, we'll discuss generally accepted guidelines for working safely with this type of equipment. The principal hazards found in work with power transformers include explosion and fire as a result of transformer failure, energizing of the transformer case due to grounding system failure, shock from exposed bushings and conductors, backfeed from low voltage sources, work on the wrong equipment due to improper labeling, failure due to draining insulating materials from an energized transformer, failure due to changing tap position under load on an energized transformer, mechanical hazards from fans, pumps, and other auxiliary equipment, failure due to adding fluid to an energized transformer when fluids are at the coil and core level, and finally, failure due to using the wrong type of fluid or by using contaminated fluid. So as you can easily see, work with power transformers can be hazardous if proper safety precautions are not followed. The rating of a power transformer depends on its voltage and the load it handles, the way it's cooled, and its auxiliary equipment, tap changers and bushing arrangements. Some power transformers make minor changes in voltage by the use of tap changes. Depending on the application, they can be designed to change voltage for single-phase or three-phase operations. And all power transformers share a basic design. A laminated square core of steel, specially made for this application, is wound with a primary and a secondary of insulated wire. The windings may be on top of each other or on opposite sides of the core. The capacity of the transformer is determined by the amount of cooling and the size of the winding conductors. Copper is the most commonly used conductor, though some aluminum is also found. A typical three-phase transformer has 6 sets of conduction coils, as shown here. The voltage change is determined by the ratio of the number of turns on each side. In this example of a step-up transformer, the primary side of the transformer has 100 turns and is fed by a 120-volt AC power source. The secondary side has 1,000 turns, a ratio of 1 to 10 for each phase. The voltage rating of the secondary side is 1,200 volts. For a step-down transformer, the ratio would be reversed, that is, a 10-to-1 ratio. Current losses in the steel core and the conductor coils produce heat. Some type of cooling device must be incorporated into the design of the transformer to dissipate this heat. Commercial transformers are cooled by immersion in a liquid or by air cooling. Liquid-cooled power transformers use a variety of materials for cooling. Silicon-based liquids are one type of material used. The vast majority of liquid-cooled potential transformers reduce high voltages to a lower voltage, usually 120 volts, for metering, protective relaying, control, and other applications. A potential transformer provides a voltage precisely proportional to the circuit it is connected to. In this program, we'll discuss generally accepted guidelines for working safely with this type of equipment. There are 3 types of potential transformers: metering transformers, protective device transformers, and control power transformers. Metering transformers are used for very precise measurement of voltage. Electrical utilities depend on these metering transformers for determining power flow through a particular commercial circuit. Protective device transformers do not require the precision of metering transformers. A common application of protective device transformers is to provide a low-voltage source for protective relay operation and metering where accuracy is not critical. Control power transformers are less expensive and physically larger than other types of potential transformers. They are used for lighting, battery charging, heating, control power, and other similar applications. In selecting a potential transformer, keep in mind the total load of the circuit in which it is to be used. Too heavy a load on the secondary side of a potential transformer can greatly reduce its accuracy and lead to total failure of the device. Backfeed through potential transformers is one of the greatest sources of shock hazards in industrial and commercial power systems. Potential transformers are often part of a complex interlock and control system. The opportunity Current transformers are a vital part of the electrical protective system in the plant. Current transformers reduce the current in the power circuit to a level that can be handled by protective relays and meters, thereby isolating them from the power circuit. In this program, we'll discuss generally accepted safe guidelines for work with this type of equipment. Hazardous situations associated with work on current transformers include failure to check the transformer before installation. The correct type and rating transformer must be used, and the secondary circuit must be complete before the transformer is energized. Opening the secondary circuit while the transformer is under load. This causes a very high voltage on the secondary side that can produce severe shock, arcing, and blast hazards. Under no circumstances should the secondary circuit of a current transformer be opened while the primary is carrying current. Current transformers are used in electrical power systems to step down current. A current transformer's primary purpose is to provide a proportional measurement of the quantity of current flowing in the circuit. The unit of current measurement is in amperes. It would be impractical and very dangerous to measure the full circuit load. Current transformers step down the current in precise Power distribution systems provide efficient distribution of electrical power throughout industrial facilities. They also provide a safe means for reducing voltages and isolating large electrical circuits. In this program, we'll discuss generally accepted safe work practices for work on power distribution systems. Clearing the system before beginning any work is very important. If positive steps are not taken to clear the part of the system you're working on, then you must consider the work as being energized. To clear part of an electrical system where work is to be done, the following steps are required. First, review operating one-line diagrams and identify all power sources that are part of the system you're working on. Second, open circuit breakers and rack out if necessary. Open switches. Remove potential transformer fuses, and take any other action needed to put a visible air gap between all power sources of the system you're going to work on. Third, use a high-voltage sensing device to verify that the system in question is de-energized, as well as the proper use of appropriate measuring equipment. And fourth, if at all possible, ground the system. The most frequent cause of injury when working on power distribution systems involves working on the Motor control centers are designed to house electrical equipment that start and stop motors, provide overload protection, interrupt short-circuit conditions on motor leads, and allow local or remote operation of contactors. In this program, we'll cover generally accepted safe work practices for working with this type of equipment. Check your location standards and the manufacturer's recommended procedures before doing any work on motor control centers. All equipment must be clearly labeled and accurate. Up-to-date one-line diagrams must be available for safe work on this equipment. And be sure you're working on the correct equipment. Identify, test, lock, tag, and try all remote sources of energy before work is done on a motor control center. Be sure that all mechanical interlocks have functioned properly. These devices are designed to prevent access to the motor control center unless the load side is de-energized first. Identify all electrical interlocks. Electrical interlocks are designed to de-energize the control power if access is attempted without first isolating the motor load. Have all tools and personal protective equipment available and on site before work is begun. Open circuit breakers, fused switches, and contactors before removing or replacing them. Be sure fuses are de-energized before pulling or replacing them. Contactors have many of the same design characteristics of circuit breakers, such as arc chutes, contacts, and plug-in fingers. However, contactors are not designed to interrupt heavy fault currents. Instead, fuses are used to protect the system from damage when fault conditions occur. Contactors are closed by manual operation of a remote control device, which energizes a coil. Once closed, they're held closed by this coil. Should a loss of power occur, the coil will release the contactor to the open position. All contactors have arc chutes that interrupt arcs during fault conditions. The arc chutes on contactors are smaller than those found on circuit breakers and should be visually checked following each fault condition and during routine maintenance. This should be performed while the contactor is de-energized and isolated from all control and backfeed power sources. A regular maintenance schedule must be established for contactors. The timing of maintenance depends on the frequency of operation rather than a fixed time schedule. Manufacturer specifications will indicate the need for maintenance on these devices. Let's review in detail the safe work practice for maintenance of contactors. Before removing or installing contactors, check that all possible sources of control power have been disconnected. This requires one of the more reliable types of overcurrent protective devices is the fuse. The fundamental element of a fuse consists of a fusible link or links enclosed in a tube and connected to contact terminals. The electrical resistance of the link is very low, and it acts as a conductor. When current in the circuit exceeds the fuse size, the link melts and opens the circuit to protect the conductors, other circuit components, and equipment. In this program, we'll discuss the various types of fuses in use today, explain how they work, illustrate how they're tested, look at the types of service they are used in, as well as safety precautions to follow when working with fuses. The voltage rating of a fuse determines the ability of the fuse to suppress the internal arcing that occurs after a fuse link melts and an arc is produced. If a fuse is used that has a voltage rating lower than the circuit voltage, arc suppression will be impaired. Under some fault current conditions, the fuse may not safely clear. All fuses have specific ampere ratings. When selecting the ampacity of a fuse, consideration must be given to the type of load it carries and molded case circuit breakers are commonly used devices for low voltage circuit protection. They're available in a wide range of sizes and ratings and have many applications. Molded case circuit breakers are normally used where a resettable circuit interrupting device is needed. In this program, we're going to look at the major components of molded case circuit breakers. Identify the 4 trip elements used in molded case circuit breakers. Identify 4 commonly performed tests on molded case circuit breakers, and discuss generally accepted guidelines for working safely with this type of equipment. The trip element on a conventional breaker uses bimetallic and electromagnets to provide overload or short circuit protection. This type of protection is called thermal magnetic protection and is an industry standard. Let's look at both the thermal and the magnetic operating positions of the trip element to see how they work. Thermal trip action is achieved through the use of bimetal strips heated by the load current. A bimetal strip consists of 2 strips of dissimilar metal bonded together. Each strip has a different thermal. Vacuum-type circuit breakers provide 3 outstanding features. They provide maximum dielectric strength. They have a long operating life, and they require very little maintenance. In this program, we're going to look at vacuum-type circuit breakers. We'll identify the major components. We'll describe the operation, and we'll discuss safety considerations to follow when working around this type of equipment. A vacuum is an excellent medium for interrupting a flow of current. In vacuum circuit breakers, contacts are drawn apart in a chamber from which air has been removed. When the contacts of a vacuum circuit breaker are closed, current flows through the interrupter. When a trip occurs, the contacts separate very quickly. An arc is drawn between the contact surfaces and is rapidly moved around a slotted electrode surface by a self-induced magnetic effect. This rapid movement limits the amount of electrode erosion and prevents the formation of hot spots on the surface of the electrode. The arc burns in an ionized metal vapor, which continually leaves the contact area and condenses on the surrounding metal shield. At an early current zero, the arc is extinguished and vapor production stops. The oil tank on oil-filled circuit breakers hold the insulating fluid that provides the insulating and interrupting medium. The voltage level and interrupting capacity determines the volume of oil and the number of tanks that are used. The oil must be free of contaminants and have high dielectric strength. Special electrical tests are used to determine the oil's suitability. Some oil-filled circuit breakers use bayonet-type contacts. These provide good surface contact with longer service life than standard butt contacts. The contacts consist of a rod which serves as the moving contact. The rod fits into a circular cluster of stationary contact fingers. The tips of the moving rod and stationary cluster serve as arcing contacts. They're made of harder, less conductive material than the main portion of the contacts. The contacts must be properly aligned, adjusted, and maintained in order for the breaker to carry normal load current without thermally damaging itself. The arc interrupter of an oil-filled circuit breaker is made of an insulating material that surrounds the contacts and extinguishes the arc. When an arc is formed, the pressure created by the arc is retained inside the interrupter. As the breaker opens and the contacts separate, the moving contact passes through the interrupter. Sulfur hexafluoride circuit breakers provide an excellent insulating medium for arc interruption. Sulfur hexafluoride gas has a dielectric strength that is 2.5 times greater than that of air. In this program, we'll look at the major components that make up sulfur hexafluoride type circuit breakers, as well as pointing out generally accepted safe work practices for this type of equipment. The bushings in sulfur hexafluoride circuit breakers are designed with their porcelain center exposed to the main breaker tank, which is filled with SF6 gas. Since the porcelain is under low pressure, the gas will flow outward in the event of a pinhole crack. This will preserve the insulating qualities of the bushing until repairs can be made. The main purpose of the bushing is to provide an electrical path from the breaker to the connecting bus. Some bushings may be insulated with sulfur hexafluoride gas. Caution: if the bushings contain sulfur hexafluoride gas, extreme care must be exercised during installation or removal. Any shock or strain on the bushings could cause them to rupture. The interrupters contain the hexafluoride gas and house the stationary contact assembly and the moving.